All right, we are diving straight into one of the deepest, weirdest mysteries in all of physics. It's a phenomenon that acts like a ghost in the machine of reality itself. I mean, what if the tiny particles that make up everything, what if they could just ignore the rules of space and time? Disappearing from one spot and then, boom, reappearing somewhere else, instantly. Yeah, it sounds totally impossible, but a really bizarre quantum experience suggests that reality is way, way stranger than we think. Okay, so to really get what's going on, we've got to talk about the rules. First, the rules of our everyday world, and then how the quantum world just absolutely loves to break them. It's pretty simple, right? In our world, if you throw a ball at a wall, it's going to bounce back. It's not going to go through. An object needs enough energy to get past a barrier. If the ball isn't moving fast enough to smash through the wall, well, it's just not getting through. That's classical physics for you. It's intuitive. It's how we see things every single day. But when we zoom way, way down to the level of atoms and electrons, the building blocks of literally everything, those solid, dependable rules we just talked about, yeah, they just kind of start to dissolve. And this brings us to this incredible phenomenon called quantum tunneling. So picture this. A particle shows up at a barrier that it absolutely should not have the energy to get through. And yet, there's a chance it'll just pop out on the other side. It doesn't break the barrier, it just tunnels right through, almost like the barrier wasn't even there to begin with. Now, here's the thing. This isn't just some weird theoretical quirk that physicists talk about. Quantum tunneling is absolutely essential to our existence. I mean, it's how the sun works. It's how particles get close enough to fuse and give us sunlight. It's how the electrons in the microchips that power your phone get around. It's even how we can build microscopes powerful enough to see individual atoms. This impossible, ghost-like stuff, it's happening all around us all the time. So physicists knew this ghostly tunneling thing was real. But that, of course, led them to a really simple, but really profound, next question. They asked a super simple question. How long does it actually take for a particle to tunnel through one of these barriers? I mean, it seems straightforward. If you're going to cross something, it has to take some amount of time, doesn't it? And this is where reality just completely veers off from what we'd expect. Logically, you'd think a thicker wall would take more time to cross. Simple. But that is not what the experiments showed. After the barrier gets to a certain thickness, the time it takes to tunnel just stops getting longer. It completely flatlines. This really bizarre finding, well, it opened the door to a conclusion that seems to violate the most sacred law in all of physics. So this discovery has a name. It's called the Hartman effect. It was first predicted way back in 1962, and get this, it's been confirmed over and over in experiments. And not just with tiny quantum particles, but with things like light waves and even sound waves. And this graph just illustrates the paradox perfectly. That dashed line, that's what our common sense expects. The thicker the barrier, the more time it takes. But the solid line, that's what really happens. The tunneling time goes up at first, but then it just hits a ceiling and stays there. It doesn't matter how much thicker you make the barrier. So let's connect the dots here. If the time it takes to cross a barrier stays the same, but the distance of that barrier can get longer and longer, what does that imply about the particle's speed? Well, the math points to something shocking. For a thick enough barrier, the implied speed becomes faster than light. And that's a huge, huge problem. I mean, the number one rule in physics is that nothing travels faster than light. So what gives? Is Einstein's ultimate speed limit wrong? Or is something even stranger going on here? Well, trying to solve this puzzle has led scientists down two main paths. One explanation kind of tries to put physics back in its nice, neat box. The other one, well, it suggests the box isn't even real to begin with. Okay, so the first explanation is a bit more conservative. The argument is pretty simple, actually. Maybe it's not a race. Maybe we're just measuring the wrong thing. Okay, so according to physicist Herbert Winful, the time we're measuring isn't how long it takes a particle to get from point A to point B. He says it's actually the lifetime of the energy that gets stored inside the barrier. You can think of it like a battery charging up and then releasing its energy. So from this point of view, there's no faster than light travel because nothing is really traveling in the traditional sense. Paradox solved, right? Case closed. But what if the explanation is even stranger? Because that's not the only way people are looking at this. Some physicists are convinced the Hartman effect isn't some measurement quirk. They think it's a clue, pointing to a much, much deeper truth about reality itself. This brings us to explanation number 2, which is, honestly, it's pretty mind-bending. It suggests that the particle isn't traveling at all. It doesn't go through the barrier because in a very real sense, it doesn't even travel through space. This idea is called non-spatiality, and it basically says that space, as you and I experience it, is just a stage. It's the theater where reality plays out for big things like us. But the fundamental particles, the quantum entities, they can exist off-stage, outside of space altogether. So if you look at it this way, there is no journey through the wall. The particle doesn't travel through the barrier. It simply ceases to exist on one side and then reappears on the other. There's no speed, not faster than light, not slower, because there was no travel through space. We're talking about actual, honest-to-goodness teleportation. And this all leads us to a final, really profound thought that gets to the very heart of how we see the universe. So, I want to leave you with this question. If the fundamental building blocks of our entire universe can exist outside of space, then where is reality really? Whether the Hartman effect is just a measurement quirk or a peek into some non-spatial existence, it forces us to think about a pretty startling possibility, that the solid, predictable world we see every day might just be the surface layer, a stage built on top of a deeper reality where distance has no meaning and teleportation is just normal. It really makes you wonder what else is hiding just beneath the surface of what we call reality.